When you ask what's humanity's greatest invention, most people might say the wheel, others will say something like the toilet. But there is one which contributions to the world has been so impactful that it has led us to change our old perspective of reality.
I am, of course, talking about imaginary numbers. Imaginary numbers have existed for centuries, hidden in plain sight.
But it used to be a way of mathematics to tell you that whatever you're trying to solve is not possible.
It was not only until Girolamo Cardano, on his pursuit of solving the cubic equation x cubed plus 15x plus 4, realized that there must be something more than just the problem being unsolved. In the procedure of solving the cubic formula through geometry, explained in another video, Cardano found that he has a square of area 30 at size of length 5. Because that will mean the square is actually 25, Cardano will have to somehow add negative area. This is where the idea of negative square roots come from. Remember how we said that this was the way for math to tell you that there is no solution? Well, this is not the case. With a bit of guessing and checking, you can find that x equals 4 is a solution. So why didn't the procedure that worked for almost every other cubic equation didn't work for this one? Cardano avoided the complications and stated in Ars Magna that the idea of negative square root is as subtle as it is useless. 10 years later, the Italian mathematician Raffaele Bombelli picked up where Cardano left.
He realized that the square roots of negatives couldn't be either positive or negatives, so he gave them their own classification.
He saw that in Cardano's solution, two terms could be represented as some combination of an ordinary number and this new type. And this way, Bombelli figured out that two cube roots in Cardano's equation are equivalent to 2, plus and minus the square root of 1. So when he takes the final step and add them together, the negative roots cancel each other, leaving out the correct answer, 4.
So Cardano's method did work, but only if you abandon the geometric proof that created it in the first place. The conclusion was that while negative area doesn't really exist, they work as a stepping stone to reach the real solution.
The term imaginary came almost a century later, as René Descartes will popularize this term. That is why Euler will introduce them with the letter I, which represent the square root of negative 1, and then when combined with a regular number, they form complex numbers.
This allowed algebra to liberate itself from the constraints of geometry, an idea that seems ridiculous at the time, because it meant to let go of what humanity believed was the best way to represent reality. But by liberating itself from what we thought this was reality, algebra found a way to find solutions for more real problems.
In 1925, Erwin Schrödinger is looking for a wave equation that governs the behavior of quantum particles. He comes up with perhaps the most famous equation in all the history of physics, the Schrödinger equation. And what is featured in this equation is I. Now this obviously generated an uproar. Why are we putting an imaginary number in such a fundamental theory? Schrödinger himself even stated that what is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. The wave function psi is surely fundamentally a real function. Then why is it in this equation? Imaginary numbers exist in a dimension perpendicular to the real numbers. See what happens if we multiply by I. 1 by I is I by I is minus 1, minus 1 by I is minus I by I is 1. So by multiplying by I, what you're really doing is rotating by 90 degrees in the complex plane. But there is a function that makes 2 constantly repeat in the z-axis, or x-axis depending on where you study, is e to the ix. It creates a spiral, but spreading out this rotation all along the z-axis. But if you only look at the real part of the spiral, it's a cosine wave. And if you look to the imaginary one, it's a sine wave. So the two quintessential functions that describe waves are contained in e to the ix. So when Schrödinger wrote his equation, he assumes it will look more or less like e to the ix, more specifically, e to the ikx. Frederick Dyson remarked, Schrödinger added the square root of -1 to the equation and suddenly it made sense. It describes correctly everything we know about the behavior of atoms, is the root of all chemistry and most physics, and that a square root of -1 means that nature works with complex numbers, not real ones. Imaginary numbers are not only used in quantum mechanics but also in fields like electrical engineering. It is thanks to them that we were able to significantly simplify the calculation of the amplitude and phase of an electrical oscillation, such as audio signals, radio wave, or even waves used in transmitting telephone calls. This is because most electric parameters have more than one dimension, such as an AC voltage and the phase of that voltage. Complex numbers are the most convenient way to represent two-dimensional quantities.
So these so-called imaginary numbers turn out to be fundamental to our description of reality. So it's paradoxical to think that it was by disassociating math with reality is how humanity was able to reach a deeper truth.